In this video, we're going to introduce the idea of a step response. This is one of the most common occurrences in all of electronics, and it happens anytime there's some resistance and some capacitance in series. And in particular, it happens billions of times a second inside every computer. So that's why we want to study this very carefully. So the step response is something that happens in a circuit when we drive the circuit with a step voltage. That's a step voltage shown right there. And this response is going to be related closely to the natural response of an RC circuit. And if you haven't seen that video yet, I want to encourage you to take a moment and go to watch the video on the RC natural response, because I'm going to use that result right here. Now, in the RC natural response, what we had was no energy going into a circuit. We had an RC circuit like this, and there was nothing connected here. So the source was removed, and we had a C and an R, and there was a voltage on the original capacitor. There was some charge on this capacitor right here. And we worked out what's the response of the current here, and what's the response of the voltage V of t across this capacitor. And there we found that V of t equals V naught times e to the minus t over RC. So this is the natural response of an RC circuit. And now what we're going to do in the step response is we're going to actually kick this circuit with a step. We're going to make the circuit do something, add some sort of stimulus from the outside that pushes this RC circuit in some direction. And we're going to see what that means. And it's going to be related to the natural response. So Vs here starts at some voltage V naught. Then at time 0, right here, it makes a step, a sharp step up to some other voltage step, Vs. And what we want to do is we want to see what this circuit does. And again, we'll label this. We want to find out this V of t. So what's going to happen is, and in the past, before t equals 0, this circuit will be in some state, and we'll figure out what that is. And then we're going to disturb the circuit, and it's going to settle down in some new state. And that's going to be called the step response of the circuit. So our approach here is going to be to look at this. First, we're going to do this intuitively. And we'll just look at a long time ago. We'll look at a long time from now, well after the step. We'll see what the circuit's doing then. And then we'll look at we'll guess at what happens in between. So first we'll do this intuitively, and then we'll do it with the formal mathematics. So I said we're going to break it down into three things. And the first thing we're going to look at is long ago. What was this circuit doing yesterday when it was sitting here at V naught? Well, long ago, Vs equals V naught. And what was going to happen is some sort of current was going to flow out of here and around into this capacitor, and it's going to leave some charge here. And that charge is going to pile up on the capacitor. And we know that it's related to the voltage on the capacitor by CV. One of the things we're going to do as we analyze this circuit is track what happens to this Q. That's a good approach to thinking about what's going on here. So if a long time ago Vs was V0, basically what happened? Some current flowed until what? Till V here reached V0. So V equals V0. At some time in the past, V became V naught. And what happened to I? Then I went to 0. And the reason we know I went to 0 is because the voltage across this resistor, let me label it like this. We'll call it VR. Eventually, this side was V naught, and this side became V naught. And that's 0 volts across the resistor, so that means the current goes to 0. So this is the state a long time ago. I want to start sketching this. We'll do some time plots of this. And we'll make this I and this V. And so we decided a long time ago, V was V naught. And the current we decided was 0. So I can put that on there like that. So that's our long time ago. Next, what we do is we go to super long time. Let's let t go to infinity. That's a long time from now. And what's the state going to be then? Well, the Vs is going to be, the source voltage is going to be Vs. I'll tell the part between capital letters and lowercase letters here. Capital letters is a fixed voltage, and Vs is something that changes with time. And we can do the same sort of analysis. There's going to be some current that will flow. Q will build up until the voltage on the capacitor is, there'll be some current. The voltage on the capacitor will go to Vs. And the same story. The voltage across the resistor then will be 0 again, and that means that I will be 0 again. This is for a long time from now. So as we continue our intuition here, a long time from now, Vs is going to be the step voltage, big Vs. And what's I going to be? I, we decided, was going to be 0. So a long time from now, out in the future, I is going to be 0 again. Okay. So now let's go back and look at what happens between. Okay, this is after the switch happens and before a long time from now. And what we can guess, what we can estimate is that V naught is going to become Vs somehow, and that the current's going to start at 0, and it's going to do something, and it has to end up back at 0. Okay, let's get a little more detailed. Let's make some little better guesses. The moment after the step happens, the voltage on this side goes to Vs. And the voltage on this side is what? Well, the charge, there's a bunch of charge sitting here on the capacitor, and it hasn't had time to go anywhere. So if that's the case, then the voltage right after the switch changes is going to still be V naught. So that's going to be the voltage right after here is not going to jump anywhere. And that's because we physically have some charge stored on this capacitor, and it hasn't had time to go anywhere yet. That means on this side of the resistor, just after the step happens, this is going to be V naught. Oh, look, now see, now we have a voltage difference across here. So there's going to be a current. All of a sudden, there's going to be some current here. Let's scribble that in. Let's see what that does. There's going to be some sort of current that happens. And it's going to be, I is what? It's going to be Vs minus V naught divided by R. That'll be the current. We'll label the current there. That's the current we're talking about. All right, so we got our current to hop up. And now there's more charge. There's charge flowing onto our capacitor. So the capacitor voltage is going to start changing. More charge, more voltage. And what's going to happen, we can estimate this, it's going to just do something like that. I can sketch that in. More and more charge will start flowing onto this capacitor, and the voltage will gradually rise until V equals Vs, till the voltage across the resistor, again, is 0, and then the current will stop. We had a sudden step of current caused by the change in the step voltage input, and then it's going to just fade out, something like that, until the current goes back to 0. V will go from, how do I write this? We'll go from V naught, and it'll eventually become Vs. And I will have a step, and then go back to 0. So that's our intuitive understanding of how this step response will look for a driven RC circuit. And next what we'll do is we'll work this out in detail, and we'll get mathematically accurate versions of what these two curves look like.